As a last video in this series on chemical energy changes, I want to look at an industrial application of what we've just spoken about. And we're going to look at what is called or commonly known as the Haber process. Okay, the Haber process. The Haber process is a process of producing ammonia as a synthesis reaction between nitrogen and hydrogen. Now, how they get the nitrogen and hydrogen in the industries and our other processes as well. Nitrogen, for example, they get from the air, but I'm not going to look at that. I want to look at specifically the application of the theory that we just used. Now, this process therefore follows what we've looked at quite a few times: nitrogen gas plus hydrogen gas reacts, okay, to produce nitrogen trihydride. This is ammonia. Okay, this is ammonia, and if I balance this equation, I have 3 of these and 2 of those. Now, one important aspect here that is going to come into play is the enthalpy. The enthalpy for this reaction is negative 92,4 kilojoules per mole. Okay, kilojoules per mole. Now, in the industry, what they therefore do is they in a closed container, they have these 2 elements react with one another. But the problem is that the energy that exists between the nitrogen bonds are very strong. So if we were to draw the graph for our internal energies, okay, well, without referring to anything other than what we have here, what can we see? The enthalpy is negative. So remember, enthalpy is the change in my product, my internal energies of my product minus the internal energy of my reactants. Now, what this is therefore telling me is if it's negative, it means that my products will have a lower enthalpy. So I will have lower here, okay. My enthalpy of my products will be lower than the enthalpy for my reactants, enthalpy for my reactions. But the strength, the bond here is so high that we really need to add a lot of energy. So the activated complex is very high. Okay, so here's my graph. Okay, the activated complex is very high, so the activation energy is very high. So to reduce the activation energy, they use a catalyst. So a catalyst is used. So if I put in if I add a catalyst, let's actually write it and align it with red, then I'm reducing my activation energy, but still breaking the nitrogen bonds is still very high, so that even at this point we still need activation energy. That means we still need to add energy in order to get the molecules excited enough so that they will be successful collisions. Now, in order to add energy, the only way that we can really add energy is by adding heat. So this reaction occurs more or less at about 400 degrees Celsius. But now the problem is this endothermic or exothermic? Notice that I've got less internal energies than I started with. So the extra energy here, so after I've added the energy, after I've added the 400 degrees Celsius, more energy is released. So the 400 degrees is released again, and more than that. Okay, so after that there's still heat as a product. So now the problem is when there is heat as a product, it is favoring the reverse reaction. Okay, because heat is, so adding this heat to the reaction is actually favoring the reverse reaction. Yes, it causes the nitrogen bonds to break, but now because I'm adding heat to the reaction, I am actually producing more nitrogen and hydrogen than I wanted to by a decomposition of the ammonia. So obviously, to counter this favoring of the reverse reaction, they need to do something else, and what they do to counter that is they decrease the volume, they increase pressure or decrease volume. Increase the pressure. Now why does that work? Well, you'll remember that an increase in pressure favors the side with the least gas, and this is a gas, by the way. Here we've got 4 moles of gas. Okay, what that means is that this takes up double the amount of volume than this one takes up, because this one only takes up 2 moles of is only 2 moles. So on the left hand side we have 4 moles of gas. Here we've got 2 moles of gas, which means if we increase the pressure, we will favor the forward reaction. So to counter the fact that we have to add heat, which will to break the bonds that will favor the reverse reaction, we increase volume as well. Okay, but still increasing volume is really decreasing volume or increasing pressure at these quantities is really a very, very, very expensive process. So the best they can now do is to now reduce the concentration of nitrogen. Remember, if I reduce this one's concentration, then relative to this one, these will have a higher concentration. If I have an increase in concentration, the reaction will favor the opposite direction. So if I could increase this one's concentration, I will favor the forward reaction. So by decreasing the concentration on the left, I am causing a shift in the balance to, sorry, not on the left, on the right, to again favor the right. I'm decreasing this one's concentration, meaning relative to the products, the reactants have a higher concentration. Again, trying to balance out that equation, it will try and produce more products. Now the way in which they reduce the concentration on the right is obviously by taking the product out. This is the product they want to produce. So by taking this product out of the closed system, they are able to reduce the concentration. So it's not really a closed system anymore. They have to keep it a closed system because they have to increase the pressure to get this reaction to really to produce. But what they then do is through condensation, let's keep the colorful pattern, through condensation. In other words, this gas is condensed at against the sides of the container, and therefore and then extracted from the reaction vessel. Through condensation, the concentration, let me write it like this, the concentration of NH3 is reduced. And this whole process, what they do here, adding a catalyst, heats at 400 degrees to break the bonds between nitrogen, but this causes a increase in the equilibrium to the left, meaning more products are or nitrogen, sorry, not nitrogen, ammonia is decomposing back. So in order to counter that, we increase the pressure to favor the forward reaction of synthesis, but that's a very expensive process, and therefore through condensation we reduce the amount of products produced, and therefore reducing the concentration of the product in the reaction vessel. This whole process is called the Haber process. Okay, so thank you very much for watching. I'm sure you found this as interesting as it really is, and we'll see you in the next topic. Enjoy.